Now let's turn to deletion. We want to remove a node from the list. The trick is the order of 2 steps. First, we relink the chain past the node we are removing. Only then do we free it. Let's see why that order matters. Let's start with the easiest delete, the first node. It has nobody in front of it, so there is no earlier link to fix. Step 1, save. We run x becomes head. That keeps a handle on the old first node before we move head. Step 2, move. We run head becomes head arrow next. Head now names the second node. Node 10 is bypassed, but it is still in memory. We have not freed it yet. Step 3, free. We run free of x. The old first node goes back to the heap. I have ghosted it in red rather than erasing it so you can see it is gone but not forgotten. The list is now just 20. 1 pointer moved, 1 node freed, big O of 1. Here is that in C if head is null, the list is empty, so we return null. Otherwise we save head in x. Move head to head arrow next, free x, and return the new head. Save, move, free in that order. Now let's remove a node by its value somewhere in the middle. We want to delete 30 from the list 10, 20, 30, 40. To do this, we keep 2 pointers walking together. Prev is the node just before, and cur is the node we want to remove. Look at the before picture. Prev points to node 20. Cur is the victim, node 30. Node 20's next field still points to the victim. Now the after picture. We redirect 1 pointer. Prev arrow next becomes cur arrow next. So node 20's next field jumps over the victim and points straight to node 40. The victim is no longer in the chain. Then we call free on the victim and its memory goes back to the heap. The important part is the order. We relink first, then free. Your turn. We are deleting 30 from the list 10, 20, 30, 40. We hold prev, which is node 20, and cur, which is the victim, node 30. Before you look at the answer, predict 3 things. Which single pointer must change and to which address? Does the victim's own next field need changing before we free it? And what is the right order, relink first then free, or free first then relink? Think about it. This is the trap. You may want to free cur as soon as you find the victim. But the relink prev arrow next becomes cur arrow next still has to read cur arrow next. If you free the node first, that red touches memory you already gave back. This is a use after free. It can crash or quietly give you garbage. So always relink first, then free. Let's delete 30 from the list 10, 20, 30, 40. First we walk 2 pointers together, prev and cur, until cur holds the node we want. 1 hop per row. Watch the table on the left. Search step 1. Prev is at 3000, node 10. Cur is at 7000, node 20. Cur arrow data is 20. Is 20 equal to 30? No, so we advance both pointers. Search step 2. Now prev is at 7000, node 20. Cur is at 4000, node 30. Is 30 equal to 30? Yes. So node 30 is the victim and prev is the node just before it. Next we relink, then free. Now the mutation. First, relink. We run prev arrow next becomes cur arrow next. So node 20's next jumps from the victim straight to node 40. The dashed line is the old link we abandoned. Notice node 10 is still here and the victim is still in memory. We have not freed it yet. Then free, we run free of cur. The victim's memory goes back to the heap. I ghosted in red instead of erasing it. The list is now 10, 20, 40. Node 10 was kept. The whole delete is big O of n because the search is the slow part. A learning check. Suppose we delete the value 20 from 20, 25, 40. At the moment we find the victim, what are prev and cur and which line does the relink? Pause and think. Here is the answer. 20 is the head, so the special head branch runs. Prev is never used. Head becomes head arrow next, so 25 is the new head, and then we free the old head. The prev in cur walk only starts at the second node. This is delete by value, and see on this slide we handle the head case. First, the empty list. If head is null, we return null. Then the head case. If head arrow data equals k, the victim is the first node which has no node in front of it. We save the old head in X, move head to head arrow next, free X, and return the new head. Why do the head first? The general walk needs a prev node, the node just before the victim, but the head has no node in front of it. So we handle the head on its own, then walk the rest of the list on the next slide. Now the general case. The victim is not the head, so it sits deeper in the list. We set prev to head and cur to head arrow next. Then we loop, moving prev and cur forward together, while cur is not null and cur arrow data is not equal to k when the loop stops. If cur is not null, we found the victim. We run prev arrow next becomes cur arrow next to relink past it, then free cur. We return head. If the key was absent, the list is unchanged. What does this cost? The time is big O of n, because finding the node just before the victim means walking the chain. The relink itself is only big O of 1. The head case is separate because the head has no prev node to fix. Let's see the same delete in 3 aligned views. First, the plain idea. We walk prev and cur until cur is the victim. Then we redirect prev's link past the victim and release the victim's memory. The head is special because it has no prev, so it is a separate case. Next, the pointer update. In short, prev.next becomes cur.next, then free cur. And remember, we relink strictly before we free. Now the C code itself. Prev arrow next becomes cur arrow next, then free cur. It is the same 2 lines as the idea, just written in C. The key order is simple. Relink first, then free. If you reverse the 2, if you free cur and then read cur arrow next, you have a use after free. So always relink before you free. When we are done with a list, we must tear it down. Every node came from malloc, so every node needs one free. Let's trace one loop turn on 10, 20, 30. Step 1, save. We run next becomes head arrow next. This holds the successor node 20 before we free the current node. Step 2, free. We run free of head. Node 10 goes back to the heap. I ghosted in red rather than erasing it. And here is the whole point. Our saved next still holds the successor, so we did not lose the rest of the list. Step 3, advance. We run head becomes next. Head now names node 20. Then the loop repeats. It frees 20, then 30 until head becomes null. Here is the code. While head is not null, we save head arrow next and next, free head, then set head to next. If we freed head first and then read head arrow next, we would touch memory we already gave back. That is why we save next first. The cost is big O of n, 1 free per node. This is the destroy operation. Every program in this chapter ends with it, so the memory checkers report no leaks.